You know how your favorite streaming service just seems to know what you want to watch next? Well, that's all driven by algorithms, but it is definitely not magic. Today, we're going to dig into a really powerful method for designing these algorithms and, more importantly, proving that they're actually any good. It all comes down to a simple, brilliant idea. So yeah, let's get into it.
And that right there is the huge question, isn't it? I mean, we trust these algorithms with everything from our music playlists to, critical software that runs our world. But just trusting them isn't enough. We need proof. How can we be mathematically certain that one approach is better than another, not just based on a few tests, but by its very design?
Well, here it is, the core idea. Instead of just building something and then hoping for the best, you first define the fundamental principles it absolutely has to follow. You basically write the rules of the game before you even start playing. And these foundational rules? They're called axioms. Now, this idea of using a set of foundational rules, it's not new. Not at all. It actually has a surprisingly long and fascinating history that goes way beyond computer code. This is the formal name for it, axiomatic analysis. Really, it's a way of thinking that forces you to be absolutely crystal clear about your goals. Before you write a single line of code, you state, okay, whatever I build, it must satisfy these non-negotiable principles. And you can see this approach in some pretty wild places. For instance, it was famously used to analyze voting systems, trying to define axioms for what makes an election fair. But here's the catch, and this is what's so interesting. Sometimes the analysis proves that a perfect system is logically impossible. You can literally prove mathematically that some common sense rules we'd want, like fairness and consistency, just can't exist together in the same system. So, when we apply this powerful method to actually building technology today, designers usually take one of two main paths. Okay, so you can think of these two mindsets as the difference between being a detective and being an architect. The descriptive approach, that's the detective. You take a system that already exists and you work backward to figure out its hidden fundamental rules. The normative approach, though, that's the architect. You start with a blueprint of the rules you want, your axioms, and then you design a whole new system from the ground up to follow them. All right, let's make this real with a concrete example. We're going to look at a showdown between two algorithms that are both used in recommender systems. So here's the thing about any recommender system. To give you good suggestions, it first has to find people who are like you. It needs to build what they call a neighborhood of users who have similar tastes. And honestly, the quality of your recommendations depends entirely on how well that neighborhood is built. So, in one corner, we've got cosine similarity. This one is super common, a really popular method. And in the other corner, we have the query likelihood model, which is a more formal, probability-based approach. So which one is actually better at building that neighborhood? I mean, we could run 1,000 tests and compare the results, sure, but how could we prove that one is just fundamentally superior by its very nature? This is where it all comes together. This is where axiomatic analysis steps in to settle the debate once and for all. The researchers didn't just test them, they put them up against a set of fundamental, non-negotiable rules. They came up with two really common sense rules or axioms that any good neighborhood algorithm should probably follow. The first one is called self-similarity. Basically, you should always be your own closest neighbor. Sounds pretty obvious, right? The second is monotonicity. If we find a movie that two users both like, adding it to their profile should only make them seem more similar, never less. With those two rules, the competition was on. And the verdict? Well, it was stunningly clear. The super common method, cosine similarity, actually breaks both rules in certain situations. It can actually fail to see you as your own best match. It's wild. But the query likelihood model? It satisfied both rules perfectly. The axioms revealed the superior design, no guesswork needed. And that's the crucial takeaway. This analysis explained why the query likelihood model was performing better in real-world tests. It wasn't just luck. It was because its fundamental design respected the rules of what makes a good neighborhood algorithm in the first place. It was provably better. And this idea is so much bigger than just getting better movie suggestions. This is a foundational concept for building artificial intelligence that we can actually rely on.
I mean, once you start looking for it, you see this axiomatic approach everywhere in computer science. It's used to formally verify that critical software has no bugs, to build AI that can make justifiable decisions when things are uncertain, and even to structure the very knowledge that AI systems use to reason about the world. At the end of the day, that's what this is all about. It's a blueprint. It's a way of thinking that lets us engineer systems that aren't just powerful, but are also understandable, reliable, and fundamentally trustworthy.
Which, of course, leaves us with one last really important question. As AI gets woven deeper and deeper into our lives, making decisions about our health, our finances, our transportation, should this kind of rigorous, rule-based proof be a requirement? Should we start demanding that our most critical systems are built not just to work, but to be provably good?